Okay, welcome back to part 4, Barycentric Coordinates. So far, we've only really gone over definitions, and we've only proved like 2 just classical results, and so we haven't really exploited the power of barycentric coordinates. So first, so from now on, it's going to get a little more intense. So now we're going to look at vectors with barycentric coordinates. So if we have 2 points, P and Q, and their coordinates are P1, P2, P3, and Q1, Q2, Q3. Then if we have this vector which goes from P to Q, then we call this a displacement vector. And its coordinates are Q1 minus P1, comma, dot, dot, dot. So you just subtract, it's just pairwise subtraction of the coordinates. And we see that since the sum of Q1, Q2, and Q3 is 1, and the sum of P1, P2, and P3 is 1, then the sum of the coordinates in a displacement vector is equal to 0. And this is an important thing to know. The sum of the coordinates of a displacement vector is 0. Now, I'm going to be using the vector properties that I showed in part 0. So if it seems like I'm pulling anything out of nowhere, just go and watch that video where I prove the things I use. Now, in barycentric problems, or problems where we invoke barycentric coordinates, it's often nice to treat the orthocenter as the origin, because we can do that arbitrarily. And this is often used when you use just normal vectors to do geometry problems. But here we're sort of combining the methods. So now we start with a theorem. So we have the following theorem. It's called EFFT. This is an abbreviation of Evan's favorite forgotten trick, because named after Evan Chen. So consider 2 displacement vectors, MN and PQ, which have the following coordinates, and remember that the sum of these coordinates equals 0. Then they are perpendicular if and only if the following equation holds. So this is pretty messy. Now, one thing I do want to note right off the bat is that consider what we talked about before, about homogenized coordinates, or homogeneous equations. Each term in here is the product of 2 variables. And so, therefore, if we were to multiply just one of these displacement vectors, then the equation would still hold true. And more than that, we know that the sum of the coordinates of a displacement vector is a homogeneous equation, because if x plus y plus z is 0, then kx plus ky plus kz is 0. Now, it isn't very useful to sort of memorize this lengthy equation. It's better to think about why do we know this? So consider, like I said, treating the orthocenter as the origin of our vector plane. Then our vectors x, y, and z, from part 1, we defined these as linear linear combinations of the A vector, B vector, and C vector, which now have origin at the circumcenter. So we can use the properties of these vectors that we talked about in part 0. And also from part 0, we knew that if we have two vectors that are perpendicular, then their dot products are 0. So what I'm saying is that if we have x1 a vector plus y1 b vector plus z1 c vector dotted with, so this is representing the mn. This is what mn is. And notice that I'm not writing the O, but each of these has origin is centered at the circumcenter. And the vector PQ is x2 a vector plus y2b vector plus z2 c vector. So we can expand this, and it gets a little messy. So we get x1, x2 times a dot a, which is r squared. Again, that's from part 0, plus y1, y2 r squared plus z1, z2 r squared plus, and now for each combination of vectors, so let's say a dot b, and remember that we had that was equal to r squared minus c squared. Now here I'm going to shorthand this, and I'm going to write cyc and a sigma. So this stands for cyclic sum, and I don't quite feel like explaining how they work, but for equations like this, where we have a lot of symmetry and you're sort of cycling through variables, it's just a shorthand way to represent it. So for each, so r squared minus c squared over 2, that's a dot b. And we get a dot b when we have x1 times y2 plus y1 times x2. So, and so by writing the cyclic sum, this accounts for each of the 3 terms. So in the next term, we'll have an a squared here. This will be y. So basically, it goes in alphabetical order, and then it repeats. So c goes to a goes to b, b goes to c, and x goes to y goes to z, and z goes to x. That's how cyclic sums work. Now, let's think about sort of factoring this r squared here. And because we have an r squared, we have an r squared, but we have this sort of minus c squared here. So let's think about, and since this is negative, it's sort of natural to bring it to the other side. So we have, again, the cyclic sum of c squared over 2, and then this stuff. Sorry, that's a y1, x2. And here I want to note that this summation is equal to this, although without the 1/2. So notice that c squared x1 y2 plus y1 x2, that's exactly this term. And this whole equation is this cyclic sum, but times 2. So it would be nice to show that what's left on this side, which has we can factor out an r squared now. We would like to show that this is in fact equal to 0. And so now I'm going to conjoin these two cyclic sums. I wrote this one out because it was fairly simple, but I'm going to conjoin these two cyclic sums. And so now we get x1, x2 plus x1, y2 plus y1, x2. And here we can use our key fact that the sum of the coordinates in a displacement vector is equal to 0. So notice we have these two terms that have a factor of x1. And if we factor it out, we get x2 plus y2. But x2 plus y2 plus z2 is equal to 0. So x2 plus y2 equals negative z2. In other words, our cyclic sum becomes negative x1 z2 plus y1 x2. And this will actually telescope because the next term of x1 z2, x goes to y, so you would have negative y1, and z goes to x, so you would have negative y1 x2. So these cancel out. And the next term here would be z1 y2. But then the next term of, obviously this, since these were the same, then we'll have a minus y1 x2, or a minus z1 y2 here. Those cancel out. And then finally, this last term will be an x1 z2. So in fact, everything does cancel out to 0. So we're left with r squared times 0, which is just 0. And then we can multiply both sides by 2, because 0 times 2 is 0, and we get the desired result. So I think that's going to be it for this video. In the next video, we'll go over some of the properties that follow from this EFFT theorem. Thank you for watching. I'll see you in the next part.